I'm focusing on how sensitive spectral clustering is to the choice of the number of clusters. We're trying to figure out ways to make the results less dependent on that choice. It's like choosing the right number of slices for a pizza. If you choose too many or too few, your slices won't be very meaningful. We want a method that is robust, even if we slightly change the number of clusters. I see you're using SpectralClustering, spectral clustering. Let's figure out which methods will help make the results less dependent on how many clusters you select. It's like trying to improve a recipe so it tastes great even if you change a small ingredient amount. Increasing n_in it improves the k-means part, which is the final step in spectral clustering. It's like trying different starting points for finding cluster centers. However, it doesn't directly solve the problem of being sensitive to the number of clusters you initially pick. It just helps to better find cluster centers given a number of clusters, not to determine the number of clusters. Gamma in the RBF, radial basis function, kernel controls the similarity between data points. A smaller gamma means that points will be considered more similar to each other, even if they're farther apart. This will result in smoother cluster boundaries and less sensitivity to the exact number of clusters chosen. Think of it like using a wider brush. Your strokes are less precise, but the overall painting is more robust to slight adjustments. Dimensionality reduction, such as PCA, principal component analysis, simplifies the data by reducing the number of features while preserving important information. Think of it like condensing a long, detailed story into a concise summary. Removing noise and less important information can make the clustering less sensitive to the number of clusters you're choosing. Changing the eigen_solver, the method used to find eigenvectors, mainly affects how quickly the algorithm runs, not how sensitive it is to the initial choice of the number of clusters. The solver is more like the engine of the car. It's important for speed, but doesn't directly influence the destination. This means more than one of the approaches could help make the clustering more stable and less sensitive to the number of clusters you've selected. This question asks how to make the results of spectral clustering less dependent on the choice of the number of clusters, NCLUSTERS. I'm looking for ways to make the algorithm more robust and less sensitive to this parameter. It's a common problem in clustering. You might find that a small change in NCLUSTERS dramatically alters the results. That's what I'm trying to avoid. Gamma controls the width of the radial basis function, RBF, kernel. A smaller gamma means a wider kernel, increasing the similarity between data points that are further apart. Think of it like this. A small makes the clustering blurrier, smoothing out the boundaries between clusters. This helps the algorithm become less picky about the precise number of clusters. A slight change in NCLUSTERS won't have as much impact because the clusters aren't so sharply defined. Principal component analysis, PCA, is a dimensionality reduction technique. It simplifies the data by focusing on the most important features and reducing noise. By removing irrelevant information, PCA makes the clustering task easier and clearer. Spectral clustering then becomes less sensitive to the initial number of clusters because the simplified data provides a clearer structure that's less influenced by minor variations. Increasing NINIT improves the k-means part of the spectral clustering algorithm. K-means is the final step and it runs multiple times with different random starting points. This helps to avoid local optima, which means you are more likely to find the best solution given the chosen number of clusters. However, this strategy won't magically fix the sensitivity to your initial choice of NCLUSTERS. The problem lies in the spectral embedding. This only improves the final clustering. The eigen_solver parameter determines the method used to find the eigenvectors of the similarity matrix. Changing the solver might improve computational efficiency or numerical accuracy, but it does not directly address the sensitivity to the chosen number of clusters, NCLUSTERS. The choice of solver doesn't change the underlying issue. I'm tackling a problem where scikit-learn's spectral clustering is too sensitive to the number of clusters I specify. I want to make it more robust, less fussy about that parameter. So I'm exploring strategies to improve its stability. The parameter gamma controls the width of the radial basis function, RBF, kernel. A smaller gamma means a wider kernel, making data points seem more similar. This blurring effect helps make the cluster boundaries less sharp, making the results less dependent on the exact number of clusters I pick. Think of it like softening the edges of your clusters. Less precise boundaries mean less sensitivity to the total number of clusters. Principal Component Analysis, PCA, simplifies data by focusing on the most important features. By removing noise and irrelevant information, PCA helps spectral clustering see the bigger picture, making it less sensitive to the number of clusters. It's like cleaning up the data before clustering, thus, improving the robustness. Increasing NINIT, number of times K means runs, makes K means more reliable, but it doesn't directly address the sensitivity to the number of clusters. It just improves the K-means part, which is the final step in spectral clustering. That means you are only improving the final step of the algorithm. The eigen_solver parameter only changes how the algorithm computes the eigenvectors. It doesn't affect the sensitivity to the number of clusters. It's like picking a different tool to do the same job. Changing tools won't impact the output's sensitivity to the number of clusters. I'm exploring how sensitive SpectralClustering is to the number of clusters we choose. It's like trying to group people into teams. If I don't pick the right number of teams, I might end up with some teams that are too big or too small, and the groupings just won't feel right. That's the problem we are trying to solve. The RBF kernel, radial basis function, uses GAMMA to determine how quickly similarity between data points decreases as their distance grows. Think of it like the range of influence of each point. A smaller GAMMA means a broader range. Points are considered similar even if they're farther apart. This can make the clustering results less dependent on the precise number of clusters you set. It's like widening the lens of our camera. We get a less focused image, but the blurring reduces the influence of small changes. Dimensionality reduction using PCA, Principal Component Analysis, simplifies your data by removing less important information, noise and irrelevant features. It's like cleaning up a messy room before organizing it. You're left with only the essential stuff, making clustering more efficient and less sensitive to the number of groups. Removing noise means that tiny variations in the data won't so strongly affect our clustering results. NINIT controls how many times KMEANS, the final clustering step in SpectralClustering, runs with different starting points. Increasing it improves the chance of finding a good solution, but it doesn't directly help with the problem of choosing the correct number of clusters in the first place. It's like trying different starting points in a maze. It will help you find a better solution in the maze, but does not help you to design the maze itself. The EIGENSOLVER parameter just deals with how the math is done. Changing it might change the speed or accuracy of the calculations, but it won't directly make your choice of the number of clusters more robust. It's like choosing a different calculator for solving a math problem. The answer doesn't depend on which calculator you use. This statement introduces the core problem. The number of clusters significantly impacts the results of spectral clustering, making it unreliable. We need strategies to make the results less sensitive to this parameter. I found that decreasing gamma, the parameter that controls the width of the Gaussian kernel in the RBF kernel, radial basis function, helps. A smaller gamma makes the kernel wider, creating smoother boundaries between clusters. This makes the algorithm less sensitive to changes in the number of clusters because the clusters become less distinct. It's like using a broader brush to paint. Smaller variations in brush strokes matter less to the final image. I see that using dimensionality reduction techniques like Principal Component Analysis, PCA, to reduce the number of features before running spectral clustering is another effective strategy. PCA removes noise and less important information, leaving only the most relevant features. This simplification makes the clustering more robust and less dependent on precisely choosing the number of clusters. Think of it like decluttering your workspace before starting a project. The less clutter, the easier it is to achieve the desired outcome. Increasing N_in it affects the K-means step, which is the final stage of spectral clustering. More iterations mean a better chance of finding the optimal cluster centers. However, this doesn't directly influence how the algorithm responds to the initial choice of the number of clusters. It only refines the final placement of points. It is only improving the results for a fixed number of clusters. Changing the eigen_solver. The algorithm used to find eigenvectors will change the computational efficiency and perhaps numerical accuracy. But it will not directly reduce sensitivity to the number of clusters chosen. It is not related to the choice of n_clusters. I see, you're asking about decreasing gamma, the parameter that controls the width of the radial basis function, RBF, kernel in spectral clustering. A smaller gamma value makes the kernel wider, increasing the similarity between data points. This, in turn, can create smoother cluster boundaries and reduce the impact of the specific number of clusters you choose. Think of it like using a broader brush when painting. You'll get less sensitivity to small strokes. This means that your clustering result would be more robust to changes in the n_clusters parameter. Let's talk about dimensionality reduction using PCA, principal component analysis. PCA is a technique to simplify your data by focusing only on the most important features, reducing noise and irrelevant information. By cleaning up your data with PCA, the spectral clustering will be less affected by the specific number of clusters you choose, because the algorithm will only work on the essential data components. It's like giving your clustering algorithm clearer data to work with so it is less easily confused by the choice of n_clusters . Increasing n_ in it the number of times k-means runs, primarily improves the k-means step's final result by helping find better cluster centers for a fixed number of clusters. It doesn't, however, directly address the selection of the initial number of clusters. It's like polishing the final result of a clustering, but the selection of the number of groups to start with remains unchanged. It's not directly solving your sensitivity issue to the choice of n_clusters . Changing the eigen_solver primarily affects the computational efficiency and numerical stability of the eigenvalue decomposition. Different solvers have different strengths and weaknesses, but altering this parameter doesn't inherently reduce your algorithm's sensitivity to the n_clusters parameter. The core question here is about the robustness of spectral clustering in terms of how it is sensitive to the number of clusters that you choose. Therefore, we need to carefully consider what methods could make this less sensitive.